Guys, good morning. I'm good morning. It's good evening. A very good evening to everybody. Right. So hope you're ready. Start. Almost everybody is there, I suppose. Right. Okay. So let me share my screen. Okay. Right. So if you can remember, we were seeing the isomerism, right? And we stepped into one of the fascinating types of isomerism called as tautomerism, isn't it? Right. So right. So I didn't exactly tell you what exactly is tautomerism, but can you tell me, guys, what and all you remember from what I told you? Can you just give me the points, whatever I told you, how much of you remember it? Yes, what are the points you remember? Can you tell me? Whatever you remember, like it need not be at the order. Okay, this I told first, that I told second. Whatever you remember about tautomerism, whatever I taught you, or whatever you have been taught in school. Like I just whatever the points you know. Yes, tell me.
So you told that it's something that happens in reality, like other isomerisms are theoretical,
Mm,
but
mm,
this
mm.
happens actually.
Exactly. That is one of the very good points, right? This happens in reality. That means all the other types of isomerism, say I give you one molecular formula, you will be able to write all the structures in the paper. But in reality, will they exist? That means will they be able to interconvert each other? The answer is no. But this tautomers are capable of interconverting each other into reality. Okay, that was the first point. What are the points? What is the type of tautomerism we are like we are telling there are so many types of tautomerism, but in our syllabus what tautomerism is there? What is the name of the tautomerism we have? What is the name? I told you dash tautomerism. I would say okay, dash tautomerism. What is it?
So is it keto and all?
Exactly, it's called keto-enol tautomerism, right? So basically, one ketone or an aldehyde can convert itself into an enol. Enol, we know what is enol. Double bond with an alcohol is what is called as an enol, right? Okay. So the next question is, what kind of aldehydes, or say, what is the necessary condition for an aldehyde or a ketone to show tautomerism? I told you if this condition is satisfied, yes, they will show tautomerism. What is the condition?
You should have an alpha carbon, sir.
Yeah,
Hydrogen,
no, no,
alpha
no.
hydrogen.
Exactly. I should have alpha hydrogen. Anyways, I'll have alpha carbon. Like, no matter what, whatever the type, whatever be the type of your aldehyde or ketone, you'll always have an alpha carbon. That is no doubt. But that carbon atom, does it have a hydrogen atom? That's the question, right? So if I have at least one alpha hydrogen, then yes, tautomerism is possible. Right. So I think I gave you some examples. We took benzaldehyde as an example. I told you that there are no alpha hydrogens. Right. So I hope you remember what do you mean by alpha hydrogen, so what do you mean by alpha carbon? An alpha carbon is the one which is directly attached to the functional group. Right. Say if I tell CH3, CH2, Cl, this is the functional group, and this is the carbon directly attached to the functional group. So this is my alpha carbon atom, and this is my beta carbon atom, and the next one would have been gamma, delta. I did just keep on going, right? Say in case of your aldehydes or ketones, say if I take acetone as an example, I would have right now you see this is the functional group, right? And the carbon atom directly attached with the functional group are these two, 1 and 2. So both these are alpha in this case, right? And obviously the hydrogen atoms contained by these alpha carbon atoms are what are called as alpha hydrogen atoms. And this obviously, as I told you, the necessary condition for tautomerism to exist is I should have at least one alpha hydrogen. So this definitely will give tautomerism. Okay, Right. So these are things this is just a brief introduction about tautomerism, right? So now we'll see what exactly is tautomerism. How as I told you, how exactly is that these isomers are able to interconvert to themselves, right? Okay. Now, why do I specify? Why do I specify so much on this alpha hydrogen atoms? What role does it? What role does these alpha hydrogens have so that it becomes so important for tautomerism? Right now, guys, I want you to remember one point, right? So please understand this point. The very reason why aldehydes and ketones having alpha hydrogens are able to exhibit tautomerism is because the alpha hydrogens in these compounds are acidic in nature. Right, they are acidic in nature. That means what? I can remove out of these three hydrogens, I can remove one of them as H plus. That, or say out of these three hydrogens, I'll be able to remove this as H plus. Right. So you generally don't see CH bond cleaving to give H plus, because we know what are the conditions in which I can get an acid. Right? I should have high polarity difference, high electronegativity difference, so on and so forth. But anyways, so what you have to understand is what is the role of alpha hydrogens here is that these alpha hydrogens, you see, alpha hydrogens only in aldehydes and ketones. Please be very careful. Not all alpha hydrogens. We're talking about keto-enol tautomerism, guys. So be very careful. I'm talking about the keto forms or aldehyde forms, right? Those alpha hydrogens are acidic. That means they can come out as H plus, right? Now, how do I prove it to you? Right, and you will be seeing this kind of questions not only here. Say if I go for it, there are so many other type of acidic hydrogens present in all the other types of functional groups. Right now, how will you decide whether that particular H plus, I mean that particular compound can give me H plus? How will you decide it is the question, right? So the thing is, I already taught you about the concept of conjugate bases. Did I? Do you remember something about conjugate bases? At least you remember the name, that word somewhere, conjugate base. Do you remember?
Yes, sir.
Okay. So anybody remembers what exactly is a conjugate base? Anybody wants to give me a answer? What do you mean by a conjugate base of an acid? Obviously, if an acid, I talk about conjugate base. If it's a base, I talk about the conjugate acid. Right. Tell me, what do you mean by a conjugate base? Say, if I ask you for HCl, what is the conjugate base? HCl is the acid. What is the conjugate base of HCl? At least one of you should remember. You see, you don't have to worry whether the answer is going to be correct or not. Whatever is there in your mind. No, no, not that way. It's the base which is reacting to some neutralization reaction, right? So the thing is, guys, if I have an acid, let's say for example, I take HCl, right? So from this HCl or from any acid for that matter, right? After removing H plus, whatever is remaining is what is called as the conjugate base, right? And this particular concept, the concept of conjugate bases, you will be using so many times in this particular chapter, like in general organic chemistry and in the upcoming chapters in 12th class, right? You will be using this concept of conjugate base. It's very important. Okay, so what do you mean by a conjugate base? After removing H plus, whatever is remaining is what is called as the conjugate base. So obviously, after removing H plus, I know what is going to remain.
Cl.
It's Cl minus. This is what is the conjugate base of this acid. Okay, after this acid, this is the conjugate base. Cl minus is the conjugate base. Okay, right. So now we understood what are conjugate bases, right? So now what you have to understand is with the actually I'm going to prove that this alpha hydrogens are acidic with the help of this concept, conjugate base concept, right? Now the thing is, guys, not only in this case, for any organic acid, right? For any organic acid, right? how will you check with, I mean, any organic substance, how it can give me H plus is, or say, what are the conditions in which could give me H plus is if the conjugate base is stable. If the conjugate base is stable, then I say that that particular thing can give me H plus. Okay, again, I repeat, right? So what I'm trying to tell you is that in JC, this concept of this conjugate base being stable, we generally don't use in inorganic acids, because there the criteria are different. We'll talk about it later. But what you have to understand is, if you have an organic molecule, right, and you suspect and you want to investigate whether that particular molecule can give me H plus, right? So how will you understand your, before, like without even conducting experiments, we'll be able to understand that, right? So how do we understand? This is the method. So you just remove the H plus randomly from any place you want, okay, and check whether that conjugate base is stable. Okay, the next question is, sir, how do I know whether it's stable or not? That I'll tell you, right? So for now, please understand, if there is an organic substance capable of giving me H plus, its conjugate base must be stable. Only then it can give me H plus. If the conjugate base is not stable, then that molecule is not capable of giving me H plus. Okay, I think I made my point clear. Again and again, I repeat, if the conjugate base is stable, that particular organic molecule is capable of giving me H plus. If not, if the conjugate base is not stable, then it cannot give me H plus, right? Okay, so keep this in mind.
So
right?
It is applicable only for organic acids, sir.
Yeah, generally only to not organic acids, generally to organic compounds. I should not write it as organic acids. I just say organic compounds. That will be a better way of putting it. Yes, it is applicable. It's not like it's going to be applicable only for organic compounds, but yeah, mostly we use this concept only for organic compounds, because for when I go for inorganic acids like HCl, HNO3 and stuff, there might be some other effects also, right, which decides whether it can give me H plus. Okay, right, fine. So now I told you that this alpha hydrogens in this ketones or ketones or aldehydes are acidic. Okay, now let me take this example, guys. Okay, let me take this example. Right, say I take acetone. Okay, so I took acetone. I mean, this is a ketone, right? So I obviously know that I have 6 alpha hydrogens. Say now I remove 1 alpha hydrogen. Right, that's the whole requirement, right? So if I remove, I write it like this, minus H plus. Okay. Okay, minus H plus, right? So now what will be remaining? See, if I can write it like this. Okay, see H2H, right? So H plus means what? Basically, there's a pair of electrons shared here between this carbon and this hydrogen, right? So if I'm going to take it as H plus, that means this hydrogen is going to lose its electron to carbon. So both these electrons are going to come to carbon, right? So what is going to happen? Carbon, can I say, is going to possess a negative charge, right? CH2 minus C double bond O. CH3. This is what is remaining, right? Now the question is, now this, how do I prove that this is going to be stable, right? Okay, now I'm not going to tell you the answer, but they have taught you this in school. They should have taught you this concept in school. Now tell me, how is this stable? One second, guys. Yeah, you just think of an answer by this time. I'll be back in a minute. I mean, I'm here only. I'm just checking something. Okay. Anyways, right. So guys, tell me, how do you think this particular anion is stable? I just need one word. No, wow, I know that I didn't teach you this, but given that this is taught in school, I expect your answer. That's why. Yes. What do you think? Okay, one
What
more
was the
clue also.
question?
Yeah. I'm telling this particular thing, this anion is stable. Okay, now how do you prove it is the question. What effect? I mean, I just need one word to say that this is stable. What is that word? Okay, fine. So you must have in your school, they should have taught you what are the ways. Say, if I give you two, three substances, if I give you two, three compounds having charges, say a positive charge, a negative, whatever it is, right? So now, what are all the ways in which you can decide stability? What did your school tell you? Tell me. Did you go for carbocations? Did you check for carbocation stability in your school? Do you remember at least the words
Yes, sir.
carbocation?
Yes, sir. They taught about carbocations.
Okay, carbocations. They would have thought they taught you. Say they would have given you two, three carboxylic acids, and then they told, okay, this is more acidic than this compound. This is more acidic than that compound. Something like that, right? So all this is based on basically stability, right? So what are the criterias? What do they use there? I just how is it that you don't remember, guys? It's been how long since they completed this chapter? Hmm?
Around
1 month?
2 months, sir.
2 months? Okay, then I understand. Cool. So guys, right. So we must have spoken about this particular thing, I think, in equilibrium as well as in chemical bonding. Did we speak about this particular phenomena?
Yes, sir.
That is the thing. Right. So but I think I should have told you how this works, resonance, right? So okay, actually, fine, cool. How do I go about this? Because I need to understand. Fine, first we'll speak about resonance, actually, but okay, fine, okay, cool. Right. So since we already spoke about resonance, I don't know how much you remember, but guys, resonance is a phenomenon of delocalization, right? Delocalization, or say I can just movement of pi electrons. Okay, now this is the other remember, guys, right? So resonance is a phenomenon which is where I have delocalization or say movement of pi electrons happening. Okay, now generally what can be pi electrons? Obviously the electrons which are there in the pi bond, right? Electrons in a pi bond. Oh god, okay. Or it can be electrons in the form of lone pairs, right? LP represents lone pair. You know what are lone pairs, right? And then, or it can be electrons in the form of negative charges. Okay, right? So this, okay, first you have to understand what is resonance. Resonance is just movement of pi electrons. Now the next question is, what are pi electrons? Pi electrons, nothing but it can be either the electrons which are there in the pi bond. We know what is a pi bond. Any double bond has one pi bond, one sigma bond. Triple bond has one sigma bond, two pi bonds. Anything you form after one sigma bond, first bond is always a pi bond. All that we already know, right? So, or it can be electrons form of lone pairs, right? Or it can be electrons in the form of negative charges, right? All of these things can move. That's what you need to understand, right? So we'll come back to this ketonyl tautomerism a little while, but let me concentrate on resonance. Now, since that we have already spoken about this, okay, fine. Now let me take the example of ozone, O3. Okay, so now if you look at the structure of ozone, you basically have this kind of structure. Okay, a double bond and a triple double bond and a single bond with oxygens. Right now, guys, tell me, there is okay. When I compare the bond length of this particular oxygen and the bond length of this oxygen, tell me which bond is longer or which bond is shorter. Hmm? Which OO bond is longer and which OO bond is shorter?
So the O single bond is longer.
Yeah, so it's all about the strength of the bond, isn't it? Stronger the bond, closer will be the atoms. Weaker the bond, like far away will be the atoms, right? And I know I have a single bond and a double bond. Obviously, a double bond is stronger than a single bond, no doubt about it, right? So, 1 second, guys, 1 second. Right, so what I was telling, so yeah, so obviously this is a double bond, this is a single bond, so I obviously know that this particular bond between these two oxygen is stronger because it's double bond, and this bond is weaker, right? So obviously this bond will be longer than this bond will be shorter, or in other words, I can just say that definitely you expect two different bond lengths to be existing in this molecule. Okay, but what I see in reality is, guys, right, what I see in reality is both these bond lengths are same. Okay, both these bond lengths are same. Through experiments I found out, right? So how do I account for it? The only way to account for it is by using resonance. Okay, now let me put basically you will see that there are going to be 3 lone pairs on this oxygen. Okay, and there will be 2 lone pairs on this oxygen. Okay, right. Now what will happen is, as I told you, the movement of pi electrons are going to happen, right? So it's better you all, whenever you're going to start with resonance structures, people, right? Whenever you're going to start with resonance, it's better to start with either lone pairs or the negative charges. It's always better to start from there. Don't directly start from electrons in the pi bond. Okay, right. So now you can see that there are going to be lone pairs here, right? Now this lone pair can come here, right? Now I know for a bond to be formed, I require 2 electrons, isn't it? Now you see that there are 2 electrons which are going to come here, right? And if this happens, guys, oxygen cannot accommodate 4 bonds. And if I look at this oxygen, right? So already there are 3 bonds. If one more lone pair comes and makes a bond here, this oxygen cannot hold 4 bonds. So what will happen is this pi bond which I have will go back to this oxygen in the form of a lone pair. Okay, so now if I write that structure properly, you will see that now the top oxygen had a single bond, right? And you have broken the pi bond and you have given it to the oxygen atom, right? So this oxygen atom would have had a negative charge, right? And between this oxygen and this oxygen, you have made a double bond, right? And this oxygen atom has lost a pair of electron, so this will have a positive charge, right? Okay, now what can happen? Again, you can start with the negative charge, make it come here, again, make this go here. You will end up with this structure again. Hope you understand, right? So again, I repeat what I did. I made one double bond and one single bond like this, right? Now, as I told you, the resonance is actually movement of pi electrons, which will happen, right? So now you see this lone pair is here. Now this lone pair will come here, make a double bond, and obviously the bond, the more I cannot have more than 3 bonds with oxygen, so this bond is gonna break, right? It is gonna go to this oxygen in the form of a lone pair. So what you see is you had only 2 lone pairs previously, but now you will have 3 lone pairs on this oxygen. Okay, and this had 3 lone pairs, and this is gonna have only 2 lone pairs. Okay, now again, if you want to get back the structure, just do exactly what it did in the previous case, exactly opposite of what it did in the previous case. Now you have a negative charge, put it here. Now you'll make a double bond. Again, this bond has to break. This will go to oxygen. So you will end up with this structure again, right? So what do you see is this pi bond which I have here, this pi bond which I have here is actually shifting between these two oxygen atom, between this oxygen atom and between this oxygen atom. This pi bond is moving. Is it not? So I cannot represent the structure like this. If I represent the structure like this, that means this oxygen double bond will have a shorter bond length and this oxygen single bond will have a longer bond length. But what I see in reality is that is that I can both these bond lengths are same, right? Right now, why is because now you can see that this double bond can be with this oxygen or the double bond can be with this oxygen, isn't it? Now these two together are what are called as resonance structures. Okay, now you can, like, if at all you want to actually represent ozone with the thing that with like by also noting down the point that they're going to have same bond lengths, you have to use a different structure altogether. Now the way of writing it is you put first single bond, that is constant, right? Now this pi bond is actually moving from this oxygen to this oxygen, isn't it? Now that you represent it with the help of a dotted line. Okay, so this structure is what is called as your resonance hybrid. Right, this structure, which is a combination of all the resonance structures put into one structure, is it not? Now in this structure you see there's a double bond between these two oxygens. In this structure you see the double bond is between these two oxygen. Put these structures together, you will be ending up with the resonance hybrid, and this is how you represent. This is how you represent the what is that? The dotted lines represent that the pi cloud is moving from this oxygen to this oxygen. Okay, right? Now what do you see? You obviously understand that the both these bond length, that is this bond length and this bond length, are going to be same, right? Now what do you expect? It is not exactly a double bond. It is not exact. Sorry, it is not exactly a single bond. It is not exactly a double bond. It is somewhere in between, isn't it? Now the bond length will also be in such that way, right? So what you understand is, obviously I know single bonds are longer, double bonds are shorter. So this particular bond length between these two oxygen atom will not be so small, will not be so long. It is going to be somewhere in between, right? Or you know bond order calculations. Hope you remember chemical bonding, molecular orbital theory, right? So in molecular orbital theory, if I speak about the bond order, BO, hope you remember what is bond order. Bond order talks about the number of bonds between the atoms, right? So between this oxygen atom and this oxygen atom, if you calculate the bond order will be 1.5. The bond order will be 1.5. That's what you need to understand. But again, this one you don't have to remember. I'm just telling you that this is neither a single bond nor a double bond. Okay, right? This is not the only case, guys. This is not the only way, only case where resonance can happen, right? Say it can happen in so many things. Okay, now we will spend our time, so much time on resonance in a very few, like after few classes. But now you understood, hope, hope you understand how this resonance works. Okay, guys, everybody, I want everybody to give me a yes if you understood resonance. Please give me a yes.
Yes, sir.
Okay, I have almost 8 people. Okay, 1, then
Yes, sir.
others.
Sir, can
Okay,
you
2.
explain the
So-
resonance hybrid again?
Wait. Someone asked me, can you explain me what?
Can you explain that resonance hybrid again, sir?
Sure. So what I understand. Okay. Now let me draw the resonance structures alone again. Okay. So you have one structure is this. Another structure is this. Obviously, charges will be there, positive charge, negative charge, depending on which has lost electron, which has gained electron and stuff. Right. So now this both structure, if I write these structures, that means what? There are going to be 2 different bond lengths, because one bond length due to double bond, one bond length due to single bond. Same here, one bond length due to double bond, one bond length due to single bond. Right. So they're going to be 2 different bond lengths. That's what I expect. But I saw due to resonance, this pi bond, which is here, is actually going to move between these 2 oxygen atoms. Right. Okay, so how do I represent the structure which indicates that there is going to be only one bond length? This is the way, right? So now you start with an oxygen atom, you put the single bond, another single bond, right? Now this you pi cloud you see here is going to be between this oxygen atom and this oxygen atom. This pi bond alone you represent it with the help of a dotted line. That's it. Right now, this indicates that the pi cloud is moving, and you can see that definitely there's going to be only one bond length. Okay, like between these two oxygen atom, it is neither a single bond nor a double bond. Again, between these two oxygen atom, it is neither a single bond nor double bond. So this is what is called as resonance hybrid, and these two are what are called as resonance structures. Yes, understood, Mithun? Mithun only, right? Who asked this?
Yes, sir. Yes, sir.
Yeah,
Understood.
understood. Right.
Yes.
So, guys, I think how many? Three people, right? Other than I have 6 more people. Everybody understood, people.
So resonance
Yeah.
is basically moving of pi bonds and forming
Yeah.
a different structure.
Yes, you can call it that way. Yes. But remember, whenever you're going to write resonance structures, people, right, you must move only the pi bonds. If you touch sigma bonds, you are gone. Right? Remember that you should not break any sigma bond. Only pi bonds can be broken or new pi bonds can be formed. That's it. That is the only thing you can do. None other things. Okay. Yes. Everybody understood?
Understood, sir.
Yeah. Okay. So I suppose, guys, if you don't understand, please do not hesitate to ask me again. Even if you ask me 3-4 more times, I am ready to explain you. But hope you understand. That's the point. The whole point is for you to understand. Yes, there's something in the chat. What happened? Okay, you understood. Thank you, Bhavadaran. Right. Okay, guys. Right now we understood the concept of resonance. Okay, now you understand because of this. One of the consequences of resonance, right? One of the consequences of resonance is about the bond lengths. You can see that I expect 2 different bond lengths, but in reality, I see only 1 bond length. Right, that is one of the things. There are obviously resonance is going to be used for deciding the stabilities of different species. Right now, I think I would have given you this example. Now we're talking about acids, isn't it? Now we actually started all this for proving that the alpha hydrogens are acidic in nature, right? And the only way I told you that how is it going to be acidic if I can prove that the conjugate base is stable, then yes, right? And how do you prove that it is stable? You are going to use one of the effects can be resonance. There are so many other effects. Hope you must have heard it in your school. Inductive effect, metameric effect, not metameric, mesomeric effect, hyperconjugation. The fancy words. You should have heard it in your school. At least heard it, even if you don't remember what exactly it is. Right. So one of them here is resonance. Right. So for us to okay. So now how do I decide stability with respect to resonance is the question now. Right now, please understand, people, stability is directly proportional to the number of resonance structures that molecule can possess. Right, say for example, there is a molecule which can have 4 resonance structures, right? And say some other molecule has say 6 resonance structures. So obviously the one which has more number of resonance structures are going to be more stable, right? So if you ask me, sir, why is it like this? Why is it that more number of resonance structures, more stability is due to entropy effects? Hope you remember what is entropy, right? So for stability, or remember for spontaneous processes, for stability, right, the entropy has to increase, isn't it? Right, the entropy has to increase. I told you second law of thermodynamics, if you can remember, right? The entropy of the thing should increase, right? So obviously you see something is moving here, right? If there is no resonance, there is no movement, less entropy. But if there is resonance, something is moving, so more entropy, more stability. But anyways, you don't have to, nobody is going to ask you why is it that this particular thing is true, but they will definitely test this point. Stability is directly proportional to the number of resonance structures that particular molecule can have, or that particular species can have. It need not be an always molecule, it can be even an ion. Right? It can be a positive charge, negative charge, or a neutral compound. It can be anything, right? But how do you decide stability? If I give you 2 species, 2 organic species, or even sometimes inorganic species, right? How do you compare their stabilities? I mean, if at all both of them give resonance, right? So obviously that you more the one which has more number of resonance structures is going to be more stable. Okay, now it's not like every molecule, wherever you see pi bonds, you cannot shift it. No. Right. Now, what you have to understand is the conditions for resonance to happen. That's what I'm telling. Okay. Now, first one is obviously I need pi electrons, no doubt about it. Right? Pi bonds or some other pi electron should be there. Right. And what you have to understand is it's not just pi electron. The better way of writing this would be they should have alternate pi electrons. What do you mean by alternate pi electrons? Let me tell you. Now, if you look at ozone's structure, right? Now you see a single bond and a double bond, right? A single bond and a double bond. So you see, first there's a double bond and there is no double bond. Again, I can say something like this. Say I have CH2. Now you can even take the conjugate base, which I took, CH2 minus C double bond O CH3. Now, if you look at here, there is a pi electron, no pi electron, again pi electron. Hope you understand. Right? Again, I see one pi electron, two pi electrons, no pi electron. Again, you see there is a pi electron here. Okay, so you should have first condition for resonance to happen is you should have alternate pi electron present in some form, either in the form of lone pair or in the form of pi bond or in the form of negative charge. But somehow, I should have a pi electron, alternate pi electron. Okay, now next condition is, right? So you see the pi cloud is moving. Say you saw that the pi cloud in the case of ozone is moving from first. What will happen basically? Right? Do you see this oxygen atom was there? Right? The lone pair was there here, and this lone pair is going here and making a bond. Correct. So what do you think? Obviously, this oxygen atom, right? This oxygen atom which I'm talking about should have empty p, or some kind of empty orbitals, so that these two electrons can be accommodated here. Again, I repeat, right? So you see that the pi cloud is moving. Okay, fine, absolutely all right. Right now, okay, this has lone pair, so it is donating. Now, for this lone pair to go, I should have some space, isn't it? Now, that's what do you mean by space? Obviously, electrons can be placed only in orbitals, right? So this oxygen atom should have an empty orbital, and now in general, it will generally be only empty p orbitals or empty d orbitals. Okay, so the next condition is I should have empty orbitals. Okay, right? Empty orbitals should be there. Anyways, you don't have to worry much about this. It's pretty easy if you understand, right? So in generally we use only carbon atoms in organic chemistry. Like what you have to understand is if you see that the carbon atom is sp2 hybridized or if it is sp hybridized, then it's completely all right. Right? If the carbon atom is sp2 hybridized or sp hybridized, it's perfectly all right. Okay, now why is it like this? If it was sp3 hybridized, right? I know there is only one s orbital, and how many p orbitals are there in total for any this thing? Obviously 3 p orbitals. So if it is sp3, all the orbitals are filled, right? But if it is sp2, one s orbital and 2 p orbitals, so one of the p orbital is still empty. Same way, when I go for sp, one s orbital, one p orbital, totally there are 3 p orbitals. So I can say that 2 p orbitals are empty, isn't it? Right? So anyways, you don't have to worry much about it, guys. Right? So now these are the conditions for resonance. You should have alternate pi electrons present, and obviously wherever the electron is going, that particular element or atom should have an empty orbital.
So I have a doubt. So that means for sp3 d orbital.
Carbon doesn't have a d orbital, right?
So for sp3 resonance
no resonance. If all the carbon atoms in the molecule are sp3 hybridized, no chance that I can have higher resonance happening. No chance. Say for example, if I have ethane, for example, CH3, both the carbon atoms are sp3. First of all, there are no pi bonds, right? But there is no this thing. But there are no empty orbitals, and also, right? So ethane is not capable, right? Again, ethene is it's also not capable. Why? If we talk about CH2 double bond CH2, Now tell me resonance is not possible here. Why? Look at the conditions. Empty p orbital S because it's sp2 hybrid. Guys, hope you remember how do you find the hybridization. That I forgot. Everybody remembers how to find the hybridization?
Yes, sir, you gave a formula. The
I gave
shortcut
a formula. Okay, let me see. Do you remember the formula to find the hybridization? Yes, I really expected that this will happen. Right, guys? I told you, right? Chemical bonding, if you miss, right, you are really going to suffer in organic chemistry for sure. Right? So I'll just brush up the concepts. How do you find the hybridization? Hope you remember there is something called a steric number, Sn. Right? Now that is equal to number of atoms bonded. Second, people. Right, so it's equal to number of atoms bonded to the central atom plus the number of lone pairs in the central atom. This is the formula. Right, so now if you find the steric number is 2, that means it is sp hybridized. Steric number 3, sp2 hybridized. 4, sp3 hybridized, so on and so forth. Right, now if you look at ethene molecule, if you look at this, if you look at this molecule, right, now if you use the formula for any one of the carbon atoms, you're talking about carbon atoms, any one carbon atom, both of them are going to be same. Right, so now you see the first one, steric number is equal to number of atoms bonded to the central atom. Right, the central atom here is carbon, isn't it? Central atom here is carbon. To that, how many other atoms are attached? You tell me. To this carbon, how many other atoms are attached?
2, sir. 2
How only
hydrogen.
2?
3, sir.
How 3? Okay, 3 is correct. How 3?
2 hydrogen, sir, and then the carbon.
Exactly,
carbon.
right. So obviously you see that there are 2 hydrogens attached to this carbon. Even this carbon atom is attached to this carbon only, right? Obviously there's a bond you can see, right? So obviously I have 2 hydrogen atoms and 1 carbon atom attached to each of the carbon atoms, right? So what is steric number? Steric number is, there are no lone pairs, obviously. You can check, right? There'll not be any lone pairs on this carbon. So I can easily say that this is going to be sp2 hybridized. Right, this is going to be sp2 hybridized. Now guys, if I didn't ask you this, if I didn't ask you how do you find the hybridization, nobody would have asked me, isn't it? And eventually would have nodded your things, I would have nodded your heads, and I would have gone. Right, so the thing is, I know where students will lack. Right, so that's why actually I'm able to exactly point out what will you not remember. Right, but you can make my job easier if you yourself come forward and tell me, sir, I don't know. I am not going to judge you. Right, so not only for this, you are going to be continuing with me for the next 1 year, 12th also I will only take for you. Right, so it's high time to do that you correct all this. Right, if you really want to enjoy chemistry, if you want to really learn the science, right, you really have to squeeze me, you really have to utilize me in a proper way. Right, I cannot be always asking you, okay, you remember this, you remember that. You can just tell me, sir, I don't remember. I will just help you there, right there. Now, how much time it took for me to tell you how to find the hybridization? 1 minute, 2 minutes, worth it. It's really worth it. Okay. So anyways, so we were talking about resonance. Right, so I told you that they're going to be, they should have alternate pi electron and an empty orbital. Obviously, I told you in case of carbon, only these two are the possibility. If you find that the carbon atom is sp2 hybridized or sp hybridized, then it's okay for me. Okay, right. But it's not like only these two. See, if I fine, okay, right. So now you understood something about resonance. Now let me talk about the acid part. Let me take some inorganic acids first. Okay, right. So now let me take. I think I would have taken this example at some point of time. What is the time, guys? Oh, Okay, I have 15 more minutes almost. Okay, so let me take HCl, HClO, HClO2, say HClO3, HClO4, right? So these are what are called as, oh, I didn't take it for you. Actually, I took it for the 12th class. I don't think I would have taken this example for you, right? So anyways, so all these are what are called as oxy acids. Okay, so whenever you see oxygen present in an acid, right? So those are what are called as oxy acids. So in this case, chlorine is there. So these are what are called as oxy acids of chlorine, right? Say H2SO4, H2SO3, all these are oxy acids of sulfur. HNO3, HNO2, all these are oxy acids of nitrogen. H3PO4, H3PO3, H3PO2, all these are oxy acids of phosphorus. So what you want to understand is hydrogen, a non-metal, and an oxygen. Non-metal you see is chlorine here, hydrogen and oxygen. If you see those combination or the compound is what is called as oxy acids. Okay, now if I ask you among these four acids, or say arrange these four acids in the order of their acidic strengths, if I ask you, right, now the only way you will be able to do that will be with the help of resonance and nothing else. Okay, so for obviously you need to know the structure for this for you to write the resonance structures. Okay, so let me go on about it, right? So HClO will have a structure like this: Cl double bond, sorry, so Cl and OH. This is what is HClO, right? So if you go to HClO2, you will have one double bond O with chlorine and the OH, and HClO3 will have two double bond O's with an OH, right? And HClO4 will have three double bond O's, OH. Okay, so anyways, right? So these are all the four structures of all these four acids: HClO, HClO2, HClO3, and HClO4. Okay, right. Fine. So now obviously I am going to use that term I told you, right? Or I'd say the strength of an acid. Please remember this point also, guys. We'll be using this again in organic chemistry. In this chapter itself, we'll be using. Remember this point: strength of an acid is directly proportional to the stability of the conjugate base. Okay, the strength of an acid is directly proportional to the stability of the conjugate base. That means more and more is the conjugate base to be stable, more and more is the strength of an acid. Okay, so this point also, again, how will you decide stability? Now you saw one of the criteria for stability with respect to resonance. I told you more and more is the number of resonance structures for a particular species, more and more is the stability, right? And more is the stability of the conjugate base, more and more is the strength of the acid. Okay, so three things are connected here: strength of an acid, stability of the conjugate base, and stability with resonance. So these are the connections here. Okay, fine. Now we know what is a conjugate base. After removing H plus, whatever is remaining is what is called as a conjugate base, right? So let me remove H plus from all these four acids, right? And we'll see what happens to the conjugate base. Okay, so let me remove the hydrogens in every acid. Okay, I have removed every hydrogen, right? So obviously, if I remove the hydrogen, I should have a negative charge on all these oxygen which has lost the hydrogen. Okay, right. Now tell me, guys, here in this compound, can I have resonance? Yes or no? And it's not a compound, actually. In this ion, these are the conjugate bases, isn't it? After removing H plus, these are all there, right? I'm asking, in this anion, in this charged particle, can I have resonance happening? Okay, let me take a vote. How many of you say yes? You can put it in the chat box also. I'm looking at the chat box.
Could you show the structure once again?
Yeah, sure. Wait. So this is the structure: ClO, and see this. Okay, if I can drop this. This is the structure: ClO minus. I have is resonance structure. Resonance possible with this. Okay, so don't give me a reason. Just tell me yes or no. We'll just check. Okay, So I'm just checking the chat box also. I want everybody to participate. Just tell me yes or no. In ClO minus, resonance is possible, yes or no? Quick, guys, we don't have time. We have a lot of things to see, a lot of fascinating stuff to see. Quick. It's just a guess. You don't have to think so much.
No, sir.
No, sir.
Okay, so 2 people say no. Okay, next. I have almost 7 people here. Quick, guys. Okay, 3 no. Then
No, sir.
okay, again 4 no. Okay, at least 1 more. Anybody wants to say yes? Okay, fine. So yes, your answers are correct, right? Definitely resonance structures are not possible because obviously there is pi electron. There is a pi electron in the form of a negative charge, but there are no alternate pi electrons, isn't it? So here it's absolutely not possible to have resonance, right? So what about this second one? ClO2 minus is it possible here?
Sir.
Yes,
Yes.
absolutely possible. Is it not? Say this, this pi bond, this electron can come here and this can break. Isn't it? So now in the resonance structure, if you see, you would have had a double bond here and a single bond here in the resonance structure, in the next resonance structure. So again, I can have a resonance hybrid here. Okay. So again, now here is it possible or not in the third structure?
It's possible, sir.
Absolutely possible. Here in the fourth structure, possible or not?
Possible, sir.
Yes, right. So other than this, all the other 3 has resonance structures possible. Okay, now fine. So I can definitely say that this is the least stable of them all because that doesn't have any resonance structures. More and more is the number of resonance structures, more and more is the stability of the conjugate base, more and more is the acidic strength. So HClO among these 4 is ranked 4th in the order of acidic strength. This is the least acidic, right? Okay. Now tell me, guys, among one, say this, and this, that is say ClO2 minus, ClO3 minus, ClO4 minus, where do I have maximum number of resonance structures?
The fourth one, sir.
Exactly, right. See, now you see, okay, let me take the structures properly. Right. So if I take ClO2 minus, right? So now one of the resonance structures can be, there is a negative charge. So now this can come here and this could have broken. So now another structure would be Cl. Here, this side I have double bond O, right? And this oxygen now would have gotten the negative charge. Okay, now I have a negative charge here. Now, if I would have taken Cl, this one, ClO3 minus, now say, now you break, you make this bond, now you have 2 choices, isn't it? Either you can break this or you could have broken this. Now, how many structures I will have? For this, I would have had 3 resonance structures. For this, I would have had only 2. One this and second this. Right? Now, this would have had 3. This is 1, right? Or the negative charge can be on this oxygen or the negative charge can be on this oxygen, depending on which pi bond you break. Isn't it? So this has 3 resonance structures. Now, if I go for ClO4 minus, okay, now you see the negative charge can be here on this oxygen, or it can be on this oxygen, or it can be on this oxygen, or it can be on this oxygen. So this will have 4 resonance structures, right? So now, as I told you, more and more is the number of resonance structures, more and more is the stability, and more is the stability of the conjugate base, more and more is the acidic strength, right? So now I can blindly say that HClO4 has the first rank, and HClO3 has second rank, HClO2 has the third rank, and HClO is the least of all acidic among these 4, right? Okay, now did you understand, guys, how do you use resonance in deciding the acidic strength of different acids? Did you get the point? Yes? Yes, no. Everybody understood why HClO4 is the most acidic among these four?
Because of number of structures, right, sir?
Exactly. It's about the number of resonance structures. More and more is the number of resonance structures. More and more is the stability. And more is the strength of the acid. Okay, right.
Understood.
Fine. Now, for whatever I started all this for your tautomerism, right? We'll just go back there, right? So now that you understood, right? So now you see the conjugate. Okay, this was the keto form, right? Now I told you any of these alpha hydrogens are acidic. That means they can come out as H plus. So if I write minus H plus, I would have had CH2 minus C double bond O CH3. Now tell me guys, is the resonance possible here? Yes, no?
Yes, sir.
Right, absolutely. So now this this negative charge can come here and this bond can break. Right? So how will you write the resonance structure now? The resonance structure would be like this: CH2 double bond C. Okay. Okay, C O minus single bond CH3. Right? Now we are talking about isomers, right? So isomers should have same molecular formula. Right. So you see, this was the total molecular formula. That means you have removed one hydrogen. So you have to add a hydrogen to me for me to get the structure out. Right. So basically you removed a H plus, just add a H plus. So if you add a H plus to this, obviously it is going to attack only the oxygen atom. So you see CH2 double bond C OH CH3. Now we have come to the end. This is what is my enol form. This is what is my keto form. And I just showed you now, they can interconvert to each other. And the main reason why ketones are able to do it is because their alpha hydrogens are acidic. And you remove the alpha hydrogen, make the resonance structure, sorry, have the oxygen atom have the negative charge, add the H plus, you will be ending up with the enol. You can see an ene and an alcohol, enol. Right? So this exactly is what is called as tautomerism, keto enol tautomerism. We'll take more examples in the next class maybe. Right? So now, yeah, tell me.
So here we took like the C double bond O becomes CO minus, sir.
Yes, right. C double bond O because
for CH3, can we make it C with CH3 minus, sir? That's possible.
I don't understand what you're asking. What are you asking?
Like, the single bond between CCH3, sir.
Can I told you, right? You should not break any sigma bond. No. The sigma bonds cannot be touched. This is a sigma bond, isn't it? Right? You should not touch it. Right? See, if you do that, if you're going to really do that, now the bond itself will not be there. There will not be any connection between these two carbon atoms if you do that. And again, it is not theoretically correct. You cannot break any sigma bonds during resonance. You can play only with pi electrons, no sigma electrons. Yes?
Understood, sir.
Right? Okay. So we'll take more example, people, in the next class. Right? I'll give you, so if at all I give you any ketone or any aldehyde, you just have to remove the alpha hydrogen, write the resonance structure, make oxygen to have the negative charge, and add hydrogen to the oxygen. That will give you your enol form from the keto form. Okay, so I hope I made a lot of sense today. You learned a lot of new stuff about resonance, about how do you decide whether a particular acid is strong or not, depending on the stability of the conjugate base, right? So there are a lot of other fascinating stuff to see. This entire chapter is going to be full of fascinations. So be ready, right? So next class we'll meet, guys. If there's any doubt, you can ask me or we can wind up. Is there any doubt?
I have one more doubt, sir.
Yeah.
It's not related to organic specific.
Yeah, tell me. No issues.
Like resonance is possible for any compound or only for compounds that have carbons, sir?
I told you, right? You saw the HClO4, HClO3. Does it have carbon? No. So the only thing is I should have alternate pi electrons and empty orbitals. If you have anything is capable of giving the resonance, not only organic compounds. Okay.
Yes, I understood. Thank you,
Right.
sir.
So even it's capable, like resonance is possible in case of H2SO4 or say HNO3. How? You can easily see if you look at the structure. Say I remove the say if I remove both the H plus ions from H2SO4, what will you see? Oops. Is S double bond O, O minus. Say I remove only one H plus, like, or say I remove both the H pluses, doesn't matter. So this is what is SO4 2 minus, right? Again, you can see this can come here, this can break, or say this can come here, this can break. All these things are possible. Again, resonance. Even in same case, in the case of nitrate ion, NO3 minus. If I remove the H plus, again you can see this will come here, this will break. So it is possible in any compound which has a pi bond, alternate pi electron, and which has an empty orbital. It doesn't matter whether it's organic or inorganic.
Understood, sir. Thank
Right.
you.
Okay. Thank you, guys. We'll meet again tomorrow. Also, we have a class morning 7 o'clock. We'll meet there. Right. Thank you so much.